All right, today's lesson we're going to do just a little bit more on derivatives, see some different contexts of problems that we can do. So first one, you're asked to identify locations where this function is not continuous, and then letter B, locations where it's not differentiable. Okay, I would like you to pause the video and give this a try on your own. Make sure you write why it's not continuous, like what type it is, and what type is the location of the spot where it's not differentiable. All right, hopefully you had a chance to try those on your own there. I only really see one spot right here. It's discontinuous at x equals 6, and that's because there is a jump discontinuity. All right, for letter B, points where it's not differentiable. So this is just a line. That's all differentiable, but right there, x equals 3, I'm seeing a sharp turn. So we know that sharp turns mean that the function is not differentiable. All right, next one, I think right here, x equals 4. This one's kind of a hidden one. People miss this one. That is a vertical tangent. All right, a lot of people want to say this one, but I think it's just poorly drawn. This is supposed to be a smooth curve here, so that's not one. All right, and then the other hidden one, x equals 4 is a little hidden, and then x equals 6 is hidden as well. People think, oh, I already said x equals 6, but that was for part A. It's also a point of not differentiability, and because discontinuous. So remember, if a function is not continuous, it can't be differentiable either. All right, and then x equals 8 as well, and that looks like a cusp right there. All right, next, which label points on the graph? Which label points is the slope of the graph? 0. Okay, well, 0 looks like that's a E and a B. 0 slopes. All right, positive, I think C and D if we draw tangent lines in there. And negative must be F and A. All right, let F be a function which satisfies that equation for all real numbers H. Find F prime of 2. All right, so this is kind of tough to visualize what you should be doing here. Okay, but what they're expecting you to recognize is that you are asked about a derivative, and then you see this, and this should look familiar. Okay, so I'm going to put a reminder over here for us. That f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and so you should recognize that. The only difference is there's a 2 plugged in for the x's. Okay, and that's fine. You're allowed to have that. So I'm going to write out f prime of 2 here is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Okay, and now we can't solve that limit because plug in 0, you get 0 over 0. But I can do a substitution. All right, so this is equal to the limit as h approaches 0. And then on top, I'm plugging this in, 5h minus 3h squared plus 9h cubed. And then that's all over h. Okay, and then we're just doing some algebra. All right, we can simplify by dividing everything by h. The limit as h approaches 0, we get 5 minus 3h plus 9h squared. Then you can solve by direct substitution, plug in your 0 for h, and that's going to zero out both of those terms, and you get 5. All right, this is a very AP exam way to ask the question. They can't ask you to do a derivative using the definition of derivative because they can't guarantee you're going to do that. Okay, once you learn all the shortcuts later on, you're never going to do a derivative that way again. Okay, so this is a way they can guarantee that you know what the definition of derivative is because you're expected to know that. Okay, and the only way to solve this problem is by knowing that this is equal to this, making that substitution, and then doing the work to get there. Okay, so you're definitely going to be required to know the definition of derivative. So we're going to keep on talking about that even as we learn the shorter and faster ways to do derivatives later on. All right, this is another similar process. We have another f of x plus something, x plus y in this case, is equal to this. We also told about this limit. I can see it's over h approaching 0, so that should be kind of making some things in my head. And then also they tell us use the definition of the derivative. Okay, so if they tell you what to do, make sure you do that. All right, so I'm going to start by just writing out the definition of derivative. Find f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, so I don't have something like exactly like this to plug in, but I have something close, especially right there. Okay, the letter y is just an arbitrary letter. It could be anything. It could be an h, in fact. So I'm going to rewrite this above here, and just everywhere I see a y, I'm going to plug in an h instead. So that's f of x minus 4f of h plus 9xh. All right, we're going to plug that into our limit right here. So the limit as h approaches 0, and then I'm plugging in f of x minus 4f of h plus 9xh. Then I have my minus f of x and all over h. All right, now we're just doing some algebra. So f of x and negative f of x can cancel. And then see how I have my f of h over h right here? I'm going to split that into its own limit. So I can take out the negative 4. And then I have the limit as h approaches 0 of f of h over h. And then plus, and I have this. So the limit as h approaches 0 of 9xh over h. Okay, so this one is negative 4 times, and then they told me this limit's equal to 2. So we are just plugging in that value right there. Plus, and then this one, the h's can cancel. And then I don't have anything to plug 0 into. Remember, this is h approaches 0, not x approaches 0. So don't plug in 0 and write 0. Okay, 9x is like a constant in this problem. Okay, even though it has an x to it, since h was the variable, x is treated like a constant in this. So this limit of a constant is equal to the constant. Oh, excuse me. All right, so just simplify 9x minus 8, and we have our answer there. All right, I'm going to play a little sometimes, always, never. All right, except we're going to use the words must, might, and never. Okay, so this limit is equal to 3. Okay, what you're expected to realize here is that this is the alternative form of the definition of derivative. This limit right here is equal to f prime of 5. Since x is approaching 5 and you have your 5s there, that's where we get the 5 on the inside, and that is the definition of derivative, so it's f prime. So this is saying f prime of 5 is equal to 3. And that's what letter A says. F prime of 5 is equal to 3. That must be true. All right, the next one is a direct contradiction to what we just set up here. F prime of 5 is equal to 0. Nope. F prime of 5 is equal to 3. So that's never true. All right, f of 5 is equal to 3. That's this right here. They didn't tell us what f of 5 is. Could it be equal to 3? It could be. We don't know. All right, so this is a might. All right, f is continuous at x equals 0. Well, we know there's a relationship between derivatives and continuity, but what we don't know anything about is x equals 0. We know something about x is equal to 5, but we don't know anything about x is equal to 0. So could it be continuous at 0? Yep, certainly could, but we don't know that for sure. All right, f is continuous at x equals 5. Okay, now we're talking. Okay, we know that the derivative exists at x equals 5 because the derivative is equal to 3. And if the derivative exists, that means that the function must have been continuous at x equals 5. All right, so we're up on a must here. And then this is part of the definition of continuity. The limit as x approaches 5 of f of x is equal to f of 5. All right, what this means is that f is continuous. If that equation is true, f is continuous at x equals 5, which is the same thing letter E said. And what does that mean? This must be true. All right, short and sweet today. Hope you enjoyed that one. See you on the next one.